All right, so this is a quick exponents review, just to kind of go over some of the things that can be problematic. All right, so real quick, just as a quick review on exponents. So exponents really are like something we use to simplify our work. X to the third really just means x times itself 3 times, or vice versa. If I had 2 times 2 times 2 times 2, that's 2 to the fourth, which is 16. So it's just a way that we use to simplify our work. What becomes a little bit confusing is when to use what rules. So let's look for an instance. If I had this whole long string expression here, I could rewrite this by kind of combining stuff. Bring all the threes together. If I'm multiplying them all, you can decide what order to multiply. So I have 3 of the threes and 4 of the x's, and so you could see it'd be 3 to the third times x to the fourth, and this actually can be simplified further to 27. X would stay the same to x to the fourth. Okay, so that's just a review. There's a property. It says, look, when you're adding stuff that's all alike, that's combining like terms. That's x plus x plus x is 3x. But when I multiply, I use exponents, right? So we're going to finally get into combining some like terms. So for instance, 2x, 4x equals 6x, so on, right? But if I had something like 2x plus 4y, those aren't like terms. I can't combine them, so I leave it alone, just like that. All right, so that's just a little review. So let's do an example. Let's take a look at this first example. I've got this long string, this long expression, and I can see here that a couple of these things are alike. 3x squared, I'm really only looking at the exponent part, the variable part, to tell me whether they're alike or not. So that one's alike, that one's different, this one's alike, and this one's alike. So those three right here, I could rewrite them and put those together. The other two, even though they're different from the others, they're both x to the first power, so those are like terms as well. So these three can be combined. I do nothing with the exponent. Exponent stays the same. It just remains to the second power. Versus over here, this is the first power, those stay the same. The only thing that changes is the number up front, the coefficient. So that's when we're just adding or subtracting. When we decide to multiply, things get a little bit different. There's actual names of the properties, but it doesn't matter. X squared, x to the third. Well, x squared is the same as x times x. X to the third, x times x times x. And I could write it all out and look to see that, hey, that's x to the fifth. But I could be a little faster about it. If I know that they have the same base, all I have to do is add the exponents. Same base, add the exponents, you get your answer. Here's a couple more examples. Right, you can see that. Let's apply it. Okay, so let's apply it to something a little bit more difficult. 3x squared, 2x to the fourth, the 3. I wrote them all out, prime factorization, broke it all down. But then I can kind of rearrange things. I put 3 times 2 together. I put all the x's together. 3 times 2, that's 6. And then I have 6 x's, x to the 6. Right? Now, there would be a faster way of doing this. Instead of writing it all out, I could just notice that, hey, 3 times 2, those are the two coefficients. Those can get actually multiplied. So that gets 6. And then x squared, x to the fourth, I add those two together, and I get that 6 here. Okay. There's some more examples, and I'll just show you the answers. You can pause it and take a look to see if you would have gotten the same answers. But let's talk about a different property. This is where it gets confusing. How about power to a power? Okay, so I have one base but two exponents. Well, x squared to the third power is x squared times x squared times x squared, right? X squared 3 different times. And so you can see here there's going to be a total of 6 of them. Right? If I break it all down, there's going to be 6 of them. But there's a faster method. Just multiply your exponents. Okay, so one base, 2 exponents, you multiply. Say, hey, there's going to be 3 of those, and there's 2 already, so that's 6. Here's some examples, and you can just check to see. I did a few just to kind of see. So x to the 4th to the 3rd, that's x to the 12th. Now, 3x squared. The 3 is inside the parenthesis, and so is the x. So both of these get that exponent power. That means the 3 gets to be 9x squared. I put another one in here. Look, this 3 is going to apply to the 3 and to the x. So 3 times 3 times 3 is 27. X squared to the third is x to the 6th. What happens if the 3 is outside the parenthesis? Well, it does not get the exponent. The 3 stays the same. The only thing that gets the exponent is what's inside. And then what about over here? What if only the 3 got it? Well, then only the 3 gets raised to the third power. The x squared stays the same. Okay, there's that. Last part is how do we apply this to multiplying polynomials. So Your book might show you just a distributing method, you know, to distribute this way, and that's basically what my method is. I just make a little box. If it's 2 term and 1 term, I put 2 boxes, 2 spaces here, 1 space here. I just put that, and I multiply. 2 times 3 is 6, x times x, x squared. 1 times 3 is 3, and then I put the x. Whatever's inside left over is my answer. If I come down here to a binomial, this is binomial times a binomial, so 2 terms by 2 terms. You can see I make a 2 by 2 window. It doesn't really matter which one you put up top or the side, but 2x, x, 3x, positive 2, and then one at a time I multiply them. 3 times 2 is 6, x times x, x squared. 3 times 1 is 3, and then there's x. 2 times 2 is 4, put my x. 2 times 1 is 2. And here's the cool thing about it is this top one is going to be all by itself. There's nothing else that has x squared, so I'm going to put that. These two happen to be like terms, so I just add them. 4 and a 3, they're both positive, so that's 7. And then my remainder part goes right there. Let me try something a little bit more challenging stuff that you probably see. Is let's say a trinomial times a trinomial. It can get a little bit confusing, so again, I make a window, 3 terms, so 3 this way, 3 that way. I place them all in their spots, and then one at a time I just multiply. Right, this first one, the next one, right? And once you fill all that out, again, it's really cool. This top part here is all by itself. That's the first term. These two here, these diagonals will both have a third power. Those are like terms. Add them together. These all 3 have a second power. Add them together. Get the 8. Add these 2 together. They both are like terms. And then there's the last one there. So that might be helpful. I don't know. If you need more, just let me know.